Typically, when linear regression is performed, we have some data points. And we want to draw the line of best fit through these data points. But in this video, we're going to have some data points in a circular pattern. And we want to draw the circle of best fit through these data points, along with finding the center and the radius of the circle. Looks more like an oval, but it's fine. Okay, but before we get started with that, let's undergo typical linear regression. So let's say we have 2 points, this point and this point, with the coordinates being x1, y1, and x2 and y2. Okay, well, we want to find the line of best fit through these 2 points, but we have 2 equations and 2 unknowns. So this is going to be our first equation and our second equation. And we don't know our slope, m, or our y-intercept, b. But we do know our x1 and y1 values. So we have 2 equations and 2 unknowns, allowing us to find the line of best fit through these 2 points. This could be rewritten in matrix format, so it looks up like this. It'll be x1, y1. No, not x1 and y1. It'll be x1 and x2. And then a column of 1s. Matrix multiplied by a matrix of m and b. And on the other side, we're going to have our y values. So it'll be y1 and y2. Now you notice that the first row of our second matrix, so m, is going to be multiplied by the first column of our first matrix, so x1 and x2. And the second row of our second matrix, so b, is going to be multiplied by the second column of our first matrix, so these 1s. So this will give us our 2 equations. So let me erase these circles so we can see it better. Oop, I did not mean to erase that x1. There we go. Now let's say that we have n data points. So instead of it just being x1 and x2 and y1 and y2, it's x1, x2, x3, all the way to xn, and then y1, y2, y3, all the way to yn. So it looks like this. So x1, x2, all the way to xn. And this is if we have n data points, if we have n of these points. And our column of 1s. And this will be multiplied, matrix multiplied by m and b. And on the other side, we're going to have our y value, so y1, y2, all the way to yn. Now, let's see the sizes of these matrices. So the size of this first matrix is going to be n by 2. The size of the matrix, second matrix is going to be 2 by 1. And the size of the matrix on the right-hand side is going to be the size of n by 1. Now, because the inner term of these 2 matrices on the left-hand side are the same, when we do matrix multiplication, the resulting matrix will be the size of the 2 outer terms, so n and 1. So that'll give us a matrix that size n by 1. So now we have n equations and 2 unknowns, but we want to have 2 equations and 2 unknowns. So we could do this by taking the transpose of this matrix right here. We call this matrix our design matrix, capital A. So the transpose of this will look something like this. So we have our first column of our design matrix becoming the first row of the transpose, way to xn, and the second column of the design matrix is going to become the second row of the transpose. That'll be just a row of 1s, and this will be the transpose. Now the size of the transpose matrix of our design matrix is going to be size 2 by n. Now, the design matrix multiplied by our transpose is going to give us a size of 2 by 2, and this is going to be matrix multiplied by a matrix of size 2 by 1, giving us a matrix of 2 by 1 on the left-hand side. But this is if we matrix multiply this to the left-hand side on both sides, like so. We'll go here, and this is going to go here. Now you notice that's going to be matrix multiplied to the same side on both sides, and this is because matrix multiplication is not commutative. Okay, so on the left-hand side, we have a matrix of size, well, 2 by n multiplied by n by 1, which will give us a matrix of size 2 by 1. And on the right-hand side, we're going to have our matrix of our 2 by n, or our transpose of our design matrix. Matrix multiplied by a matrix of size n by 1, giving us a matrix of size 2 by 1. So now we have two equations and two unknowns. So we can hop into Google Collaboratory and visualize this a little bit better using our beautiful plots using Plotly. So let's switch over. Okay, so first off, we need to actually generate our data points. So we can undergo doing this by, first off, we'll be performing numerical calculations with NumPy. So we're going to import NumPy as MP. And we're also going to make some subplots coming up. So from plotly.subplots, import make subplots. So we need to actually have our x and y values for all of our data points. So let's say that our x values are just going to be linearly spaced points from 0 to 5, and let's say we have n of these. And now let's say that we have 25 data points, so n is equal to 25. Now for our y values, let's say that we want it to be a slope of 2, and we want to have a y-intercept of, let's just say 1 for now. Now we don't know our original slope and intercept, and this is what we're trying to find out, but we do know our x and y values. But we actually need to first generate our data points. Now you notice that there's a period after the 2 and the 1, and this is because we want these numbers to be in floating point number. Okay, and the reasoning behind this is because we want to use decimal points coming up. We want these to be in decimal point format. Okay, so after that, we could plot this up. So we're going to create a figure. So figure is going to be equal to make subplots. And now we want to add a scatter to our figure. And let's say we want our x equal to x, x equals x, y equal y, and let's say our mode is going to be set to markers, close the parentheses, shift enter. Now we have our scatter plot of our data points. But first off, let's reformat this to make it a little bit more clear. So fig.update layout. We set the width to 600, and we can set the template to plotly dark. Oh, there we go. Dark, there we go. And now we have our data points, but you notice that the data points, they already really resemble line, and we want to jiggle them up a bit so that the y values are slightly different than our line of best fit through them. So the way that we're going to be doing this is going to be adding a random normal to our y values. So numpy.random.normal. We're going to set the average location to our expression. And we're going to set our, I guess, scale to, let's say 0.5. So the scale is going to be the standard deviation. Shift enter, and now here we go. So now we have our data points, and we want to draw the line of best fit through them. Now, before we get started with iPad method, I just wanted to put it out there that there's actually a feature in NumPy called polyfit, which actually allows us to find that missing slope and intercept for the line of best fit through these points. So numpy.polyfit is going to be x equals x, y equal y, and we're going to set our degree to 1 because the highest exponent in our equation of the line is going to be 1. So shift enter. And now we're given with an estimated, we're given back an estimated slope and an estimated y-intercept. But you notice that they're not exactly the same as entered, and this is because we had a random function with a scale of 0.5. Okay, so now let's do the method that we just did on the iPad. So first off, we actually need to define our design matrix, or capital A. And to do this, we could create a concatenate, and we're going to concatenate two columns. Our first column is just going to be our x values, and our second column is going to be a column of 1s of the same size as our x. And after this, well, we could just use the numpy.linalg.solve method in NumPy to be able to solve this for our slope and intercept. So numpy.linalg.solve, we're going to set our left-hand side to the transpose of our design matrix, matrix multiplied by our design matrix, and on the right hand side we're going to have the transpose of our design matrix, matrix multiplied by our y values. Shift enter, and notice that now this gives us the same values as if we use the polyfit function, and this would give us 1.97 and 0.977, which are going to be the estimated values for our slope and intercept. So now we could unpack this into the variables m and b, and we could plot the line of best fit. So we just copy down the scatter function, and we can set the y, instead of just being set back to y, we can set the y to m, our estimated slope, times our x values, plus b, our estimated y-intercept, and set the mode to lines instead. And shift enter. And there we go. So we have our data points, and we drew the line of best fit through them using linear regression. Now, going back to our original idea. So we have some data points in a circular pattern, and we want to draw the circle of best fit through these data points. along with finding the center and the radius of the circle. So to start out this, well, we need the equation of circle. So the equation of circle is going to be x minus x naught squared plus y minus y naught squared. That's going to be equal to r squared, with x naught and y naught being the center of the circle and r being the radius. Well, we know our x and y values, but we don't know our x naught, y naught, and r squared values. So we can actually expand this out. So to do this, just x squared minus 2x x naught plus x naught squared plus y squared minus 2y y naught plus y naught squared, and it's going to be equal to r squared. Now remember that we do know our x naught and y naught values, so we can move these all to one side and move all the terms that we don't know to the other side. So we don't know our r squared, so we subtract that to both sides, and we can subtract x naught squared and y naught. We can subtract x squared and y squared to both sides, so that we have all the terms that we do know on one side and all the terms that we don't know on the other side. So doing that would give us minus 2x x naught plus, minus 2y y naught plus x naught squared plus y naught squared minus r squared, and that's going to be equal to minus x squared minus y squared. Okay, so now just like what we did before, we could expand this out into matrix form. So once we do that, it will look something like this. So our first matrix is going to be minus 2x1 minus 2x2 all the way to minus 2xn if we have n data points. And now we have minus 2y1 minus 2y2 all the way to minus 2yn. Now we can have a column of 1s. There we go. And this is going to be matrix multiplied by a matrix with x naught, y naught, and x naught squared plus y naught squared minus r squared. Now you notice that after we solve this using linear regression, after we solve this using linear algebra, we're going to be given the values for x naught and y naught, the center of the circle. Along with that, we can find out the radius using the information that we find using the center of the circle. Okay, and on the other side, we're going to have a matrix of our x, of our minus x squared and minus y squared. So it'll just be minus x1 squared minus y1 squared minus x2 squared minus y2 squared all the way to minus xn squared minus yn squared. There we go. So now, oh, there we go. Sorry, I cannot zoom out for a second, but there we go. So for the size of the matrices is going to be n by 3. The size of the second matrix is going to be 3 by 1, and the matrix, the size of the matrix on the right-hand side is just going to be n by 1. Now you notice that after matrix multiplication on the left-hand side, we're going to have a matrix of size n by 1. So now we have n equations and 3 unknowns, but we want to have 3 equations and 3 unknowns. So to do this, we could do what we just did basically above, previously for traditional linear regression, typical linear regression, and by taking the transpose of this design matrix right here. So this one right here, we're going to call this A. Once again, we could erase this circle now that we have determined that, and we can also get rid of these sizes so that we have a little bit more space to work with. So the transpose of our design matrix, capital A, is going to be like this. So it'll be minus 2x1 minus 2x2 all the way to minus 2xn. And our second row is going to be minus 2y1 minus 2y2 all the way to minus 2yn. And our third row is just going to be a row of 1s. There we go. So this is going to be our transpose of our design matrix. Now once again, we're going to matrix multiply this to both sides on the left-hand side. So we're going to matrix multiply it here and here. And the reasoning behind this is because matrix multiplication is not commutative. Okay, so now for the sizes of these matrices. Well, the transpose is going to have a size of 3 by n. The size of this of our design matrix is going to have size of n by 3. So that'll give us a matrix of size 3 by 3. This then is going to be matrix multiplied by a matrix of size 3 by 1, which will give us a matrix of size 3 by 1. And on the other side, on the right-hand side, we're going to have our transpose of our design matrix, matrix of size 3 by n, matrix multiplied by a matrix of size n by 1, which will give us a matrix of size 3 by 1. So now we have our 3 equations and 3 unknowns, and this would allow us to find our center, and using that we could find our radius. So let's go back to Collaboratory and plot this out. But first off, we need to actually generate our data points. And to generate our data points, we're going to be using this thing called polar coordinates. Okay. So the way that polar coordinates is that we have our center. And we have a radius. And this radius basically just goes all around the circle, like so. And at certain theta degrees, right? So let's say this is going to be theta degrees. It's going to place a point. And then now this is theta degrees, still will place another point. And now this is theta degrees, so we'll place another point. And this is how we're going to be generating our data points. So let's hop into Collaboratory. And let me bring my pencil here so I could hopefully better explain this once we get to it. Okay, so now first off, what we need to do is generate our data points. And like how I said earlier, we're going to be using some polar coordinates. So first off, we need to define our theta degrees. So theta is going to be, well, let's just say that for now we want it to be linearly spaced points from 0 to 2 pi. These would be 2 pi radians in a circle, in an entire revolution of a circle. And let's say we have n data points once again, and we can define n up here as, let's just say 35 this time. Why not? Okay, so now after this, we have to define our radius. So for our radius, we want a radius that is changing. So every single point varies a certain distance away from the center. So to do this, we could just use a random normal function in NumPy, and we could have the average location be 3 with a standard deviation of, let's say, I don't know, 0.2, and we could set our size being n, since we want n of these points. Okay, so now we have to get our x and y values. Well, remember, let me go back to the iPad for a second, sitting down here. So remember, sine is going to be opposite over hypotenuse, and the cosine is going to be adjacent over hypotenuse. Well, hypotenuse is just going to be radius the entire time, so that would just be r. So if we have r times the sine of theta, right, that'll just give us the vertical values. And likewise for our cosine, but this would give us our horizontal values. That'll be our x, and that'll be our y and x values respectively. So for our x values, that'll be r, our radius, going to be multiplied by the cosine of theta. And let's say that we want to shift this a little bit to the right. Let's just say we shift this by 2. Remember, there's going to be a period there because we're going to be working in decimal points coming up. And for the y, we're going to have the radius being multiplied by the sine of theta, because sine is going to be opposite over hypotenuse. And we're going to have this shifted upwards by, let's say, 1. So we're going to be having a center in the first quadrant. Okay, so after this, we could just simply plot this up. So we could just copy and paste this plot from up here down here and shift enter. Now you notice that it looks a little bit funky, and the reasoning behind this is because the width and the height are different. So we can set them to be the same. So height is going to be equal to 600. There we go. So now we have some data points that resemble a circle better. Okay. But now after this, we could shift the, I guess, the number of theta degrees where a point is placed, because right now they're going to be linearly spaced away from the center, right? And we could shift this up by using the random normal function, and we set the average location to be our linearly spaced points from 0 to 2 pi, and we can set our scale to be 0.2, yeah, and then shift enter, and there we go. So now the points are going to be a little bit at different locations relative to each other. Okay, so now we want to draw the circle of best fit through these points, through these data points, along with finding the center and the radius. So let me scroll up on the iPad a bit. Okay, so first off, we also have to have our design matrix, so capital A, and we could just use the concatenate function once again, and this will basically just combine the columns. So our first column is going to be -2 times our x values, and then our second column is going to be -2 times our y values, and then our third column is going to be a column of 1s, the same size as either x or y, but in this case, let's just use x. Y would also work, but let's just choose x because why not? And after that, all we have to do is just do the linear algebra. So to do this, once again, we're going to be using NumPy's linear algebra solve method. So that'll just be numpy.linalg.solve. And on our left-hand side, we're going to have our transpose of our design matrix multiplied by our design matrix. And on the right-hand side, we're going to have the transpose of our design matrix multiplied by our by this, I guess, combination of our x and y values. So parentheses minus x, and we're actually just going to place an extra parentheses just in case if what's the thing called, if it does get canceled out where the negative sign is locked in with the x, and that's going to be squared. So we can just do it here. So x squared, and this will be minus parentheses y squared. Okay, and I think we need another parentheses, and there we go, and shift enter. And you notice that now this gives back to us 3 values. So our first value, as shown on the iPad, will be our x naught. So that'll be our shift in the x, which will be the center. And now we have our y shift, which will be by 1.014. And then after that, we have our third term, which will be x naught squared plus y naught squared minus r squared. Now, once again, these terms are not going to be completely exact to the exact shift that we did, and that's because we randomized the values up here. Okay, so now from here, we could find our radius. So we know our center of the circle is going to be at roughly 2.02 and 1.01. So we could assign this to x naught and y naught, and we could set this, I guess, value, the third value, as like a placeholder at, let's just say, b. Okay, so where's my pen? I think I'm pretty, okay, there we go. It's just behind the iPad. So, oh, I need to recline this back up. Actually, let me just stand back up. It'll be a lot easier. Okay, so now we have b. So b is going to be equal to x naught squared plus y naught squared minus r squared. So b is going to be x naught squared plus y naught squared minus r squared. Is that right? Yeah, that is right. Okay, so now we know our x naught squared and y naught squared and b values, but we don't know our r squared value. So what we could do here is add r squared to both sides and subtract b to both sides. So that'll give us r squared is going to be equal to x naught squared plus y naught squared minus b. And we can take the square root of both sides. So r is going to be equal to square root of x naught squared plus y naught squared minus b. There we go. And now we can go back to co-laboratory. Put the pen up here so I don't lose it again. And now we can actually find our estimated radius. So our estimated radius is going to be a square root, numpy.sqrt, square root of x naught squared plus y naught squared minus b, that placeholder value that we assigned above. So shift enter. And let's take a look at our estimated radius. And notice that it is 2.95, which is very close to the average radius that we set here. But once again, it's not going to be completely exact because we randomized it over here. Okay, so now we can plot up our, I guess, circle of best fit. But we want to use the values that we found down here. We don't want to use the values that we assigned to actually make the data points. So we could copy and paste down our plot. But we want theta plot, instead of it being equal to instead of it just being equal to the random normal and setting it to a location of that and then having a standard deviation of that, we're just going to set it to the linearly spaced points, and we're going to set it from 0 to 2 pi to not be pi, and we're going to have 360 points. Okay, and now after this, we're gonna have to get our r, x, and y. So our r here is going to be we can just call this r fit, so we don't actually override the value that we assigned here in case we ever want to use that again. So we could reassign this to be r fit. And now for x and y values, well, our x and y values here, we just multiplied the radius that we actually manually assigned here, to the cosine of the theta. But this is what we already have here. But we want to actually use what we actually found over here. So we want to find out the theta plot, and we want to use our r fit instead of using our r and cosine of direct theta. So we could just set x is going to be equal to r fit, our radius, times the cosine of theta plot. Okay, and then we're going to have our shift in the x direction, or x naught. And then for our y values, we're going to have our r fit being multiplied by the sine of theta plot. And this is going to be added by our y naught values. Okay, and we can set this, instead of it just being x and y, we could just set it to x fit and y fit, so we don't override the variables that we assigned up here in case we ever want to use those again. So just copy and paste this down here. Set x to be x fit, y equals y fit, and instead of the mode being set to markers, we can set this to lines, and shift enter. And now we have the circle of best fit for our circularly shaped data points as a pattern. We also know the center, and we also know the radius. Now you might ask, once we finish this, right, what makes this linear regression?
Well, we transformed a question that would not usually be linear regression into a format which we could use linear algebra, principles to solve it. So therefore, it's going to be linear regression. So now we have the circle of best fit for our data points. And there you go. Thank you for watching.